Okay, so moving on to lecture 5, we're going to talk a little bit about truth tables. So we're going to continue our discussion of logic and talk about truth tables. So in the previous lecture, in lecture 4, we talked about statements, connectives, and quantifiers. So we talked about what a statement is. So remember, a statement is in logic anyway, a statement is a declarative sentence that is either true or false. And then we talked about connectives, right? So simple statements just convey a single idea. Compound statements contain several ideas that are combined together, and we combine these with connectives. And so the different kinds of connectives that we had were negation, conjunction, which is like conveys the idea of and, disjunction, which conveys the idea of or, conditional, which conveys the idea of if then, and then biconditional, which conveys the notion of if and only if, right? Or equivalence. We're gonna, in this section, we're gonna talk about truth tables. And the reason we're gonna talk about truth tables is because they help us to determine when two statements are equivalent. Like these two statements, so the statement not P and Q is equivalent to the statement not P or not Q. Right? They convey exactly the same meaning, and to see why, we'll use some truth tables. So in this lecture, we're only going to talk about truth tables with these three connectives: negation, conjunction, and disjunction. In lecture 6, in the next lecture, we'll talk about truth tables with conditional and biconditionals, right? And we'll talk about I don't know why that was so hard for me to think of, but anyway, conditionals and biconditionals, and we'll talk a little bit more about what conditionals and biconditionals mean. So anyway, so let's get into it. Let's talk about negation. So negation in logic works exactly like negation in everyday language, okay? Or at least in the English language, right? So like in Spanish, for example, double negatives don't necessarily make a positive, but they do in English. Anyway, so negation in logic works exactly like negation in everyday English, right? So if R is true, then not R is false. And then similarly, if Q is false, then not Q is true. So for example, if R is the statement 2 plus 2 equals 4, then not R would be the statement 2 plus 2 does not equal 4. And that's a false statement because, of course, 2 plus 2 does equal 4, right? So 2 plus 2 does not equal 4. That's a false statement, right? So if R is true, then not R is false. Similarly, if Q is false, then not Q is going to be true, right? So if Q is the statement George Washington was the King of England, that's false, right? George Washington was the general of the Continental Army. He was the first president of the United States, at least under the present Constitution that we have, right? So not under the Articles of Confederation, but he was the first president of the United States as we know it. But he was not the King of England, right? This is a false statement. George Washington was the King of England. That's false. So what would not Q say? Not Q would say George Washington was not the King of England. Right? And that's a true statement because he wasn't the King of England. So not Q is a true statement. George Washington was not the King of England. Right? That's true. Okay. So for example, let's determine whether the statement is true or false and then state its negation. So part A says the Dallas Cowboys are a well-known football team. I would say that's a true statement. I think most people, or at least most Americans, have heard of the Dallas Cowboys. So we'll say that this is a true statement, right? This statement is true. Well, this is true. So that's the first thing we're supposed to do, to determine whether the statement is true or false. Well, the statement's true. Then the next thing we're supposed to do is state the negation of the statement. So the statement is the Dallas Cowboys are a well-known football team. I might call that statement W, right? For W for well-known, right? So then the question is, what is the statement not W? What would that say? Well, if W is the statement the Dallas Cowboys are a well-known football team, then not W would be the Dallas Cowboys are not a well-known football team, right? Are not a well-known football team. Okay? All right. So the Dallas Cowboys are a well-known football team. That's a true statement. The Dallas Cowboys are not a well-known football team. Well, I would say that's false, right? Because again, I think most people, most Americans anyway, have heard of the Dallas Cowboys, and they know that they're a football team. Okay. So yeah, so notice that the negation of each statement has the opposite truth value of the original statement. So the original statement here was true. Its negation is false. All right. Part B. Mexico is a prosperous country in Asia. Okay. Well, that's a false statement, right? Because Mexico is not in Asia. Mexico is in North America, right? It's right on our southern border. So no, that's not a true statement. That's very badly false, right? So this is false. This is false. You didn't know that you would take a math class and learn geography, right? But if you didn't know that Mexico is the country that borders us on the south, then I think you've got some problems. But no, this is a false statement, right? So Mexico is a prosperous country in Asia. False, right? Let's call this statement M for Mexico, right? So Mexico is a prosperous country in Asia. So what would the negation be? So not M. Well, there are a couple ways you could negate it. And actually, there are kind of two claims that are being made about Mexico. Well, maybe more than two, right? You could say one claims that Mexico is prosperous, another claims that Mexico is a country, and another claims that Mexico is in Asia. So which one of those things are we supposed to negate? It's not entirely clear. So maybe the best way to negate this statement is to just negate the whole thing and say, it is not the case that Mexico is a prosperous country. In Asia, right? So it is not the case that Mexico is a prosperous country in Asia. That would be one way to negate it. So that's that one, right? And then, of course, that would be a true statement, right? It's not the case that Mexico is a prosperous country in Asia, because maybe Mexico is a prosperous country in North America, right? And Mexico is maybe, in certain ways, it's maybe not as prosperous as the United States is, but it's certainly more prosperous than other countries, right? It's not a terrible place to be. Anyway, so that's that. Now here's how we arrange these things into a truth table. So when you make a truth table, first of all, you make a column for every statement, every simple statement that's in the overall statement, and then you make another column for whatever kind of connective that you're performing in order to join those simple statements. So in the case of negation, we can negate just a single statement, and that single statement might be true or it might be false. Okay, so in the entries in the table, we put the truth values, right? Whether the statement is true or false, and so the statement could be true or it could be false. If the original statement's true, then its negation is false. If the original statement is false, then its negation is true. So that's how we would complete a truth table for negation, for the operation of negation. Okay. That's negation. Let's talk about conjunction. Okay, so the and connective also works in logic the way it does in everyday life. So when you say, I'm a basketball fan and I like rock music, then you're saying that both conditions are true, both statements are true, right? So I am a basketball fan has to be true, and I like rock music has to be true. In order for the overall statement to be true, both of the simple statements have to be true, right? This statement is of the form P and Q, where P is the statement, I am a basketball fan, and Q is the statement, I like rock music. We could have chosen different letters, maybe B and R. B for basketball, R for rock music. I don't know. But anyway, the only way you're telling the truth is if both P and Q are true, right? They both have to be true in order for P and Q to be true. All right? So let's determine whether each statement is true or false. So this first one says J.K. Rowling is a well-known author, J.K. Rowling is a well-known writer, and U2 is a famous rock band. So in order for the overall statement to be true, each piece has to be true, right? So is it true that J.K. Rowling is a well-known writer? Yeah, I would say so. She wrote Harry Potter, right? I think most people have probably heard of J.K. Rowling. What about U2 is a famous rock band? Now this one maybe dates me a little bit. So maybe some of you have never heard of U2. But if you ask most people, I would say if you ask most people over the age of 30, they would say yes, of course, U2 is a famous rock band. So I say true and true. So is the statement true? Like, yes, the statement is true, right? So this little statement is true. This little statement is true. So we say yes, the statement is true. Okay. What about the next one? It says Shaquille O'Neal played first base for the Atlanta Braves, and he refuses to do TV commercials. This statement is false, right? So Shaquille O'Neal was a basketball player, right? So he did not play first base for the Atlanta Braves. He didn't play baseball, right? Or, I mean, maybe he played baseball as a kid or something. I don't know a whole lot about Shaquille O'Neal's life. But he certainly didn't play for the Atlanta Braves. He didn't play Major League Baseball. So no, this is a false statement. Which means we can stop thinking about this automatically, because if the first piece is false, then the whole thing is false, right? But just for the sake of argument, the second little simple statement is also false, right? He refuses to do TV commercials. Now, he's done a couple TV commercials. I can't remember off the top of my head, but I know I've seen him in some commercials, right? So this is false on both counts. So we'd say, so determine whether the statement is true or false. I don't know why I said yes here. We would just say, determine whether the statement is true or false. We would say the statement is true. Here we would say the statement is false. Okay, and then part C, it says, when you are 50 years old, you will be a billionaire, and Maine is larger than California. Okay, so this one is kind of interesting. It says, when you're 50 years old, you will be a billionaire. That one actually, so that little simple statement, I mean, who knows, right? I'm not 50 yet. Maybe I'll be a billionaire by that time. And some of you listening might be 50 already, and so you may know whether this is true or false. Maybe you're a billionaire, and maybe you're not. But a lot of you who are watching this probably aren't 50 years old yet, and so you don't know. Maybe you'll be a billionaire. Who knows, right? So that we don't know the truth value of that. What about the second piece? It says Maine is larger than California. Well, now that we know is definitely false, right? California is bigger than Maine. Maine is a relatively small state. California is the third largest state in the United States. So California is larger than Maine. That makes that second simple statement a false statement. So even though we don't know the truth value of the first statement, we definitely know that the truth value of the overall, the compound statement, is false, because the second simple statement is false. So we can say definitively that the statement is false. Okay? Regardless of whether or not you're going to be a billionaire when you're 50. This statement is false because the second piece is false. Okay. Here's how a truth table would look for a conjunction. Okay, so first of all, again, you make a column for each simple statement. In this case, for a conjunction, you have to have at least two simple statements, right? So we'll call those P and Q. And then you list all of the possible truth values for those things. Now, each of the individual statements can only be true or false. So you might ask yourself, why do we have 4 rows? But it's because you have to list all of the possible combinations of truth values, right? So one possible combination is that both statements are true. Another possible combination is that P is true but Q is false. Another possible combination is that P is false but Q is true. And then finally, another possible combination is that P is false and Q is false, right? So what I want to point out to you is that an easy way to get this pattern is to just do the first one T, T, F, F, and then do the second one alternating TF, TF, right? And then you'll get the pattern. But anyway, so if we're thinking about P and Q, so if P is true and Q is true, then P and Q is true. If P is true and Q is false, then P and Q is false, right? As we saw in part C up here. If P is false and Q is true, then P and Q is, again, false. And then finally, if F is false and Q is false, then P and Q is false, right? As we saw in parts A and B of the previous example. Or not part A, I guess, just part B, right? So this one was kind of like part A. This one was kind of like part B. And this one was kind of like part C. We didn't really see or actually it would have been, this one was kind of like part C, right? But we didn't really have an example of the second one, but it's similar to part C, right? Anyway, so yeah, that's how a truth table looks for conjunction. Let's talk about disjunction. Okay. Now, disjunction takes a little bit of explanation. Okay, so logicians and mathematicians use the word or slightly differently than the way it's used in everyday life. So in everyday language, we usually use what's called the exclusive or, which means one or the other but not both. For example, if I said you will have a quiz on Tuesday or Thursday, then you would expect to have a quiz on one of those days, but not both days, right? You would expect to have a quiz on Tuesday, but not on Thursday. Or you would expect to have a quiz on Thursday, but not on Tuesday. So that's the exclusive or. And that's how we tend to use the word or in everyday language. In logic, though, we use the inclusive or, right? The inclusive or, which means one or the other or possibly both. So in logic, the statement, you will have a quiz on Tuesday or Thursday, means that you could have a quiz on Tuesday only, or you could have a quiz on Thursday only, or you could have a quiz on both days, right? You could have a quiz on both Tuesday and Thursday. So in logic, that's what we mean when we say or. We mean one or the other or both, okay? So just be aware of that as you're going through these exercises. So let's consider an example together. It says, consider the following help wanted ad. So it says, management trainee wanted. Applicant must have 4-year degree in accounting or 3 years of experience working in a financial institution. Okay, which applicant should be considered for the position if we interpret or as we do in logic? Okay, so in other words, we're going to be using the inclusive or. So part A says, Aya has a 4-year degree in accounting and has worked 2 years for a loan company. Okay. Well, in order for an applicant to be considered for the position, they need to either have a 4-year degree in accounting or they need to have 3 years of experience working in a financial institution, or both, right? Aya has a 4-year degree in accounting. So she qualifies, right? Automatically she qualifies. It doesn't even matter what the rest of her experience is. It says, she's worked 2 years for a loan company. Well, so she has 2 years of experience working for a financial institution. She was supposed to have 3, right? But it doesn't matter because she's already qualified because she meets the first criterion, right? she has a 4-year degree in accounting. So because she has a 4-year degree in accounting, she should be considered for the position, right? We'll say she only has 2 years of experience. Right? She only has 2 years of experience, not 3. But because she has a 4-year degree in accounting, she is qualified and should be considered for the position. Okay, so she should be considered for sure. By the way, if you need to pause the video and kind of catch up to what I write down, obviously you're free to do so. Okay, part B says, Heidi has studied accounting in college but did not graduate and has worked for 5 years selling electronics. Okay, so she's studied some accounting, but she doesn't have a 4-year degree, so she doesn't meet the first criterion. That's okay, though. As long as she has 3 years of experience working in a financial institution, she should still be considered for the job. Does she have at least 3 years of experience working in a financial institution? Well, it says she's worked for 5 years selling electronics. So, no, right? Because selling electronics is not the same thing as working for a financial institution. She might work at Radio Shack or something, but but that doesn't mean that she knows anything about, accounting or finance or anything like that. So so Heidi doesn't meet either criterion. She doesn't have a 4-year degree. In accounting. And she doesn't have 3 years experience at a financial institution. She should not be considered for the job. Okay. Very good. Part C. Monty earned a 4-year degree in accounting, so he's qualified automatically, right? So Monty earned a 4-year degree in accounting and has 5 years of experience working for a credit card company. Well, so he meets both criteria, right? Monty meets both criteria. Okay, and remember that or means one or the other or both. And so since he meets both criteria, he should be considered for the job. Monty meets both criteria, so he should be considered for the job. Okay, and that's that. So so hopefully that helps you understand how OR works with logic. So let's talk about the truth table then. All right. So again, in order to have an OR connective, this disjunction, we have to have at least 2 statements, P and Q, and we need to list off all of the possible combinations of those 2 statements. So I'm going to do the same thing as before: true, true, false, false, and then true, false, true, false. And that way you get every possible combination of true and false. Now let's think about P or Q. If P is true and Q is true, then P or Q is true. If P is true and Q is false, then P or Q is still true, right? If P is false and Q is true, then P or Q is still true, right? Because all you need is for at least one of them to be true. So at least one or both, right? And then if P is false and Q is false, then P or Q is false. So the only way P or Q can be false is if both P and Q are false, okay? So now compare that to the truth table for conjunction, right? Where a conjunction is almost always false, right? The only way a conjunction can be true is if both P and Q are true. If even one of them is false, then the conjunction is false. Whereas with the disjunction, right, it's almost always true, right? All you need is for at least one of the statements to be true for the conjunction to be true. Or sorry, for the disjunction to be true. Okay. So now let's talk about some compound statements. So now that we've talked about negation, conjunction, and disjunction, we can kind of put these things together to determine the truth value of a very complicated statement. The first step in doing so is to list all the possible combinations of truth values for each simple statement. And from now on, I'm going to call simple statements variables. So we want to list all the possible combinations of truth values for each variable in the compound statement. So if the statement has one variable, so if it's just a simple statement, then the truth value, or truth table, will have 2 to the first power lines. So 2 lines, right? So if it's just P, then it's going to have true or false. If the statement has 2 variables, P and Q, then the truth table will have 2 squared, right? So in other words, 4 lines, right? And we've seen this several times already, okay? What if the statement has 3 variables? We'll call them P, Q, and R. Well, notice if it has 3 variables, then in order to get all the possible combinations, you would have to say, well, they can all 3 be true, or maybe P and Q are true, R is false, or maybe P and R are true, Q is false, or maybe P is false, but Q and R are true, right? So that's if they're all true, and then we have 3 possibilities if one of them is false. Well, what if 2 of them are false? That could be true, false, false. It could be false, true, false, or it could be false, false, true. So 3 possibilities there. And then finally, there's the possibility that all 3 of them are false. So if you count up all of these possibilities, you get 1, 2, 3, 4, 5, 6, 7, 8. Well, that just so happens to be 2 cubed. So going back, you notice this pattern, right? If there's 1 variable, then the truth value has 2 to the 1 lines. If there's 2 variables, then the truth table has 2 to the 2 lines. If there are 3 variables, then the truth table has 2 to the 3 lines. Okay? And so forth. So if you had in general, if you had k variables, then the truth table would have 2 to the k lines. Another thing that I'll point out is, we talked about this pattern, true, true, false, false, and then true, false, true, false. Notice that here, that pattern still holds with Q and R, but it's repeated twice. So you have true, true, false, false, and then true, true, false, false again. And then true, false, true, false, true, false, true, false. But because you have a third variable, then you have to have a third pattern of true, 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 false, 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 false. So generally, the pattern is this, right? The first variable in your table, you put half of the lines true, and then half of the lines false. Okay? And then for the next variable in the table, you do half of the half true, and then the other half false, and then you repeat that. Okay? And then for the third one, you alternate, right? True, false, true, false, true, false, true, false. So anyway, however you prefer to think about it is fine, but you just need to make sure that you list all 8 possibilities if you have 3 variables. If you have 4 variables, 2 to the 4th power is 16, so you'd have 16 lines. If you have 5 variables, 2 to the 5th power is 32, so you'd have 32 lines, and you need to list off all 32 possibilities. I don't imagine things getting that crazy, but anyway, that's how it would work. So example 4 says, compute a truth table for a statement of the form not P and Q, or P and Q. Okay. So the first step in making our truth table, so this is the end goal. This is what we want to end up at. Okay? In order to get here, first we need to know what not P and Q is. And in order to know what not P and Q is, we need to know what not P is. We also need to know what P and Q is. So there's going to be a couple steps that we need to take before we're able to get to this disjunction, this OR. All right? But the very first step is to list off, it looks like there are only two variables, P and Q. P and Q. So there are only two variables for this particular truth table. And so we'll have P and Q, and then we'll have some other stuff. So for P and Q, let's see. We can have true, true, false, false. Try to give yourself, plenty of space so that you don't get confused with the lines. And then true, false, true, false. So those are all of the possible combinations of P and Q. Now again, this is where I'm trying to end up. So if you think through the process, it's like, in order to end up with this OR, first I need to do this AND, not P and Q. I also need to do this AND, P and Q. But in order to do this first AND, not P and Q, I first need to know what not P is. So I'm going to make another column for not P. Let's see what not P is. Well, if P is true, then not P is false. If P is true, then not P is false. If P is false, then not P is true. If P is false, then not P is true. Okay. Now I can make a column for not P and Q. All right, so for this first one, not P and Q. So I'm going to look at these two columns, not P and Q. And remember, in order for not P and Q to be true, we need for both of the things to be true. So here, not P is false, Q is true. That means not P and Q is false. Here, not P is false and Q is false. That means not P and Q is false. Here, not P is true, Q is true. So not P and Q is true. And here, not P is true, Q is false. So not P and Q is false. Okay? So again, in order for a conjunction to be true, both statements have to be true. Here, one of them was false. Here, they were both false. Here, they were both true. So the conjunction was true. And here, one of them was false. Again, we're looking at these two columns, right? These two columns, not P and Q. Okay, now let's do this other conjunction, P and Q. Okay, so P and Q. Let's see. So for P and Q, we're going to compare the first two columns, P and Q. All right? Again, in order for the conjunction to be true, both variables have to be true. So here they're both true. That means the conjunction is true. Here one of them is false, so the conjunction is false. Here one of them is false, so the conjunction is false. And here both of them are false, so the conjunction is false. Finally, and I'm going to put like a double column here. Maybe I'll put a double column here as well, because like these were our original variables, and this was just some scratch work. And now this is the final result that we were hoping to get to, was not P and Q, or P and Q. All right, so this is the final statement that we were trying to arrive at. And in order to do this now, we're going to look at the not P, we're going to look at the not P and Q column, and then we're going to look at the P and Q column. And this time we're doing a disjunction, right? So in order for the disjunction to be true, we only need for one of these columns to be true, at least one of them, right? So one or two or both. So the only way this disjunction is going to be false is if both columns are false. So for this first row, we have one true statement, so that means the disjunction is true. For the second column, or second row, we have both false statements, so that means that the disjunction is false. In this row, we have one true and one false, but that means that the disjunction is going to be true. And for this one, we have both false, so that means the disjunction is going to be false. Okay, and that's our truth table. So you may think, well, this is all just a bunch of symbols, right? What does all this stuff mean? Well, what this means is that if both P and Q, so remember, we're boiling this down to just the simple statements P and Q. And if both of those simple statements are true, then this complicated statement is going to be true. If P is true but Q is false, then this complicated statement is going to be false. Okay? If P is false but Q is true, then this complicated statement is going to be true. Okay, so that's kind of interesting. And then if P and Q are both false, then the complicated statement is false. All right, so that's what that means. Okay, let's do another one. Ooh, this time we're going to have 3 variables, P, Q, and R. 3 variables, but I think probably less scratch work. We'll see. So P, Q, R, and then I'll do a little double bar. You don't have to do the double bar. I just like it. I think it makes things more clear, at least for me personally. And then obviously, I didn't do a very good job drawing straight lines here, but the straighter you can draw the lines, the easier it's going to be to keep track of everything. So try to draw straight lines. You could use a ruler. You might be doing a lot of this work on lined paper, which would be probably a good thing. But anyway, so we've got to list all the possible combinations of truth values for P, Q, and R. So since there are 3 variables, I'm going to have 2 to the 3rd power number of lines. Well, 2 cubed is 8. So I'm going to have 8 lines, right? So for P, the first half of them, so the first 4 of them are going to be true. And then the last 4 are going to be false. Okay? So for Q, it's going to be true, true, false, false, true, true, false, false. And then for R, it's going to be true, false, true, false, true, false, true, false. And that should list all of the possibilities. It's a good idea to look back through your work and make sure you don't have any repeats of possible combinations. But that should do it. Okay? So now let's see, what do we need to figure out? Well, in order to figure out this conjunction, we first need to do this disjunction. In order to do this disjunction, we first need to do not P. So let's do not P. So if P is true, 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 false, 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 not P is just going to switch all of those truth values. So it's going to be false, 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 true, 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 true. So there's not P. And now we can do not P or Q. All right, so that's that first disjunction, not P or Q. So for not P or Q, let me use a pencil so that I can erase it later so I don't confuse myself later. But not P or Q means I'm going to compare this column and this column. Okay, and it's a disjunction. So in order for the disjunction to be true, I only need for one of these things to be true. So here I've got one of the things is true. One of the things is true. They're both false, so the disjunction's false. They're both false, so the disjunction's false. Here they're both true, so the disjunction is true. Here they're both true, so the disjunction is true. One of them is true, so the disjunction is true. One of them is true, so the disjunction is true. Okay. So I'm going to erase those arrows now so I don't confuse myself on the next step. Now what? Okay, so we've done this disjunction, but our goal is to do this big conjunction, right? Well, in order to do that, we need to know what not R is. So I'm going to do another row, or another column, sorry, for not R. So not R is just going to switch all the truth values of R. So here it was T, so we're going to change it to F. Here it was F, so we're going to change it to T, and so forth. F, T, F, T, F, T. Okay. So now we have not P or Q, and we also have not R, so we're ready to do the conjunction, not P or Q and not R. So I'm going to do another little double bar. So I've arrived at my final statement that I wanted to make the truth table for. So it's not P or Q and not R. So for this, I'm going to compare these last two columns, not P or Q and not R. Now this is a conjunction. So in order for the conjunction to be true, we need for both columns to be true. So here we only have one true, so this is false. Here we have two true, so it's true. Here we have two false, so it's false. One false, so false. One false, so false. Both true, so true. One false, so false. And then both true, so true. Okay. And then that's it. That's the truth table, right? So this is the final goal. And again, you'll notice, well, how do you get a true statement? You get a true statement if P is true, Q is true, and R is false. Or you can get a true statement if P is false, Q is true, and R is false. That's kind of interesting. Or you can get a true statement if all three of the original simple statements are false. So if all three of them, P, Q, and R, are all false, then this overall statement is going to be true. And that might seem a little bit weird, but it's because you've got a lot of negation going on, right? Anyway, so that's that. So hopefully that gives you some sense of how truth tables work. Now, a couple more things I want to mention for this section. So two statements are logically equivalent if they have the same variables, and when their truth values are computed, the final columns in the tables are identical. Okay? So for example, it says, are the following statements logically equivalent? The first statement says, it is not true that the pasta bar accepts coupons and the deli accepts coupons. And the second statement says, the pasta bar does not accept coupons or the deli does not accept coupons. Okay, so we want to figure out if those two statements are really saying the same thing. We want to see if they are logically equivalent. And the way that we're going to determine whether or not they're logically equivalent is we're going to make truth tables for each of those statements. So in order to do that, let's assign some variables. So it says it's not true that, that's just a big negation, right? So what are they saying is not true? The pasta bar accepts coupons and the deli accepts coupons. So for the pasta bar accepts coupons, I'm going to call that P. And for the deli accepts coupons, I'm going to call that D. So let P be the pasta bar accepts coupons. And then let D be the statement that the deli accepts coupons. Okay? So making that making those switches, then we can cross some stuff out. We can say the pasta bar accepts coupons. We're going to think of that as P. The deli accepts coupons. We're going to think of that as D. It is not true that we can think of as a negation. So it's tilde. But we're negating this whole thing. And then finally, the and is a conjunction, right? So that first statement in logic symbols would just be not P and D. Okay? Meanwhile, the second statement, and I shouldn't have written this stuff so close to it, but the second statement says the pasta bar does not accept coupons. So this is like not P, right? So the first statement, the pasta bar does not accept coupons, is not P. And then the deli does not accept coupons is not D. And then or is a disjunction. So the second statement is just not P or not D. So we want to know if those two statements are the same. Is it the same? Is saying not P and D the same thing as saying not P or not D? Well, let's make truth tables. All right. So for statement 1, not P and D, the truth statement would look like this. We've got two variables, P and D. That means we're going to have 2 to the 2, or in other words, 4 lines. They're going to be T, T, F, F, and then T, F, T, F. Okay. Now, for not P and D, in order to do this negation, first we need to do the conjunction. So let's do P and D. In order for P and D to be true, we need for both P and D to be true, right? We need for both variables to be true. So here on this first row, they're both true, so the conjunction is true. Here D is false, so the conjunction is false. Here P is false, so the conjunction is false. And here they're both false, so the conjunction is false. Okay, now we can do the statement we were trying to get at, which was not P and D. That's just the negation of the previous column. So we're going to change the truth values of the previous column. So true becomes false, and false becomes true. True, true. All right. Now let's see about the second statement. Second statement is not P or not D. Okay, so again, two variables, P and D. And again, they're going to go the same way. When you're trying to determine logical equivalency, it is important that you get these combinations in the same order that you got those combinations, because we want to check to make sure that we need to see if the last columns are the same, and you have to be comparing apples to apples, so you need to have it in the same order as you did the previous one. Anyway, in order to do not P or not D, first we need to know what not P is, and then we need to know what not D is. So not P, we're going to change all the truth values of the P column. So it's going to be false, false, true, true. Okay, and then not D, we're going to change all the truth values of the second column. So it's going to be false, true, false, true. Okay, and then finally we can do this disjunction, not P or not D. Okay. So remember, in order for a disjunction to be true, you just need for at least one of the variables to be true. Now here they're both false, so this is false. Here one of them is true, so this is true. Here one of them is true, so this is true. And here they're both true, so this is true. Now, compare that last column. False, true, 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 false, true, true, true. They're the same, right? They're the same. And that means that these two statements are logically equivalent, right? So we would say, so the question was, are the following statements logically equivalent? We would say yes. The statements are logically equivalent. Right? That's the answer to the question. Now, if you think about this in words, right? Let's think about the statements again. It says, it is not true that the pasta bar accepts coupons and the deli accepts coupons. Right? So, if it's not true that that's the case, now how could that not be true? Well, it could be that the pasta bar accepts coupons, but that the deli does not. Right? So that's possible. Or it could be that the pasta bar doesn't accept coupons, but the deli does. Right? So that's possible. Or it could be that neither of them accepts coupons. Right? So in other words, it could be that not P or not D or both. Well, that's exactly what this says, right? The pasta bar does not accept coupons, or the deli does not accept coupons. And when we use or logically, it's the inclusive or. So that means not this or not that or not both, right? Not this or not that or both. So yeah, it makes sense that these two statements are saying the same thing, and you can see that now in the logic tables. Okay, so the statements are logically equivalent. Very good. Last thing I want to mention is De Morgan's laws, and this is something that will come up again in the next unit. So not in this first unit of material, but in the next unit we'll talk about set theory, and we'll talk about De Morgan's laws again when we talk about set theory. But here's De Morgan's laws for logic. So it says, if P and Q are statements, then not P and Q is logically equivalent to not P or not Q. And that's the example that we just saw on the previous page, right? But then there's another version of De Morgan's law, which says this: not P or Q is logically equivalent to not P and not Q. Okay? So you're welcome to verify this using truth tables as we did for example 6, and actually we've pretty much already verified part A, so it would be a good exercise for you to try to verify part B on your own using logic tables. But for now we'll just take it for granted, and let's practice using these laws. So example 7 says, use De Morgan's laws to rewrite the following statement, which is based on instructions for filling form 1040A with the IRS. And the statement is, it is false that you receive interest from a seller-financed mortgage and the buyer used the property as a personal residence. Okay, so when it says it is false that, that's a negation. So we're going to negate a whole big statement, right? Well, that statement is a compound statement. It says, you received interest from a seller-financed mortgage. I'm just going to call that I for interest. Okay, so I can scratch all that off. The second simple statement is, the buyer used the property as a personal residence. So I'm going to call that R for residence. And then the and, well, that's a conjunction. All right, so this statement is not I and R. Well, according to De Morgan's laws, not I and R is logically equivalent to not I and R. So if you think of this as I and you think of this as R, it's logically equivalent to not I or not R. Okay, well, what would not I look like? Well, I was the statement you received interest from a seller financed mortgage. So not I would be you did not receive interest from a seller financed mortgage. So so not I or not R would be you did not receive interest from a seller financed mortgage okay, or or not R. Well, R was the statement the buyer used the property as a personal residence. So not R would be the buyer did not use the property as a personal residence. So, or the buyer did not use the property as a personal residence. Okay? So that would be the answer to the question. All right? And you can see that, you know, this could be potentially useful. Not that you're actually going to write stuff out like this, but the more you think about this kind of stuff, the more sense it makes and the more capable you'll be of just kind of doing it in your head. So that when you read something like, you know, so I would imagine on the IRS form, it might say something like, you know, did you receive interest from a seller financed mortgage that the buyer used as a personal, you know, that the buyer used as a personal residence or something? You can kind of flip that over in your head and say, well, the answer to that question is no, right? In other words, I did not receive interest from a seller financed mortgage, or the buyer did not use the property as a personal residence. Okay, so maybe you did receive interest from a seller financed mortgage, but the buyer didn't use the property as a personal residence, or vice versa, or maybe both things are false, right? But the more you can kind of the more you look at this kind of stuff, the more you can kind of do that in your head, and then it helps you make sense of you know, stuff like this. So that's all I have to say about this section. Oh man, I've been talking for a long time.